Okay, so now let's get into this boundary layer thing. From the last lecture, I hope you all appreciate that to answer these questions, we have to zoom in to the surface of something. So just like we did a single straight pipe for internal flows, remember in internal flows, we started, sort of step one was look at a single straight pipe. For external flows, right, we're going to look at a very similar, right? So internal, we looked at single straight pipe. Now we're going to look at a single flat plate. It's remarkable how similar these things are. So we draw our picture. Right? I drew it many times, right? The whole point is here's some external inviscid flow where viscosity does not matter out here because it's going to be flowing so fast. And then over here, I know that no slip has to occur right here. Right? And then if we look at streamlines, here's the inviscid part, right, where u at some distance equals this external or far field velocity. So we have a changing velocity then, because I had to get from 0 to this value. So it looks right. We actually don't know what this function is, but just like here, here's my coordinate system. I'll call this y. I'll call this x. Same situation. We're now trying to figure out what on earth is this velocity distribution. It's a u over y. So how did I get from going from 0 to here? That's the question we're trying to answer. I'm going to say I know this for certain. I gave you all those examples of experiments that we just definitely believe in no slip, and we just definitely understand that far away, the velocity is what it looked like far field. So how did it get from point A to point E? That is the question, the burning question of boundary layers. So let's just sort of put more picture, right? Let's just sort of draw more pictures. So here's my measured length of my plate. I'm also going to say here is the boundary layer. We call it boundary layer. Right? It's a unit of meters or centimeters or whatever you want. And then what else do I have? So my parameters here are what? And the fluid flowing itself has a density and a viscosity. So list out your parameters. I have an external flow, far field flow, the air flow, etc. I have the length of my plate. I have the boundary layer, which is a parameter. We don't know it, but just like we didn't know the time constant, we're going to do stuff to figure out what delta is. What else do I know? I know the density of fluid, and I know the viscosity. So what do you think is going to happen? Well, we're going to write down the Navier-Stokes equations to write the total vectorial form one. We're going to non-dimensionalize it and plug in these bad boys. And then what's going to happen is we're going to get like very rigorous simplifications and derive the boundary layer equations. They're sort of like the baby cousins of the Navier-Stokes because they govern almost all of external flows. So, right, you can start off from the total three-dimensional Navier-Stokes equation. So, right, remember that I'm going to write this as a vector. So I'm talking about the vector velocities. So I have u. Actually, you know what? I'm just going to write it this way. You can also remember from lecture 1. Remember that material derivative? Gradient of a pressure field. And then I have my viscous force here. And what else do I have? Continuity equation. equation, right? So this is really 3 equations because they're in vector forms. You did some extra credits to see that because this is a vector, and then you have the continuity equation. And those are those are things you write down. So remember we had all those parameters. So we're all right. This is dimensional. This has dimensions to it. So to get to the equations that really matter and what really govern the dynamics of the fluid close to the surface of something in external flow, we're going to do this non-dimensionalization and we're going to compare scales. Right? So, just as I said with non-dimensionals, I like to use the scale things. So here are the scales or assumptions of boundary layer flow, right? So you say that the x-coordinate scales like the length of my plate. So let me just draw this again, and you can rewrite the Navier-Stokes equations. Personally, I think the picture is always more informative than the equation, because you just use a picture to fill in variables in equations. So this is y, this is x. See how these sort of match. These match. Clearly, there's far field. Right. So then, for our scales of this problem, I'm going to say that the x-coordinate scales like the length of my plate, which is fairly long. Right. Keep in mind this goes out. Keep in mind this goes out of the board and into the board. We'll have something to say about that too. I'll say that my y-coordinate scales like the boundary layer. I don't know this. Right, we don't know that yet. The x velocity scales like the far field, right? So the velocity going that way. I'm going to say scales like this far field velocity. We also look at the steady state for boundary layer equations. So I actually even think sometimes for steady state, I just say steady state is sort of time scaling as infinite because it's gone long enough. So you can actually plug these scales into non-dimensionalize your equations. So you'd have 1 over infinity for all the time parts that just die off. But so I kind of have an example to show you how like you can do a lot of reasoning just through scales because this is just steady state. Saying that time scale is infinity. And then the other assumption that we're going to make is that the z velocity, the velocity in and out of the board, right, is scales as like some very, very tiny number. Really 0, but again, you can't say something scales as 0 for more subtle reasons, but no, don't worry about it. This just means there's not a lot of cross flow happening. That's all just moving forward, right? So if there's a plane flying in the air, right? Most of the flow is just facing it. We don't have flow kind of cross flow over it. Or we're just going so fast in this direction that maybe there's a little bit of gust of wind, but it's like nothing much at all. Really, the dominant is the 500 miles an hour wind hitting it. So there's a lot of reason to make this justified that the in and out of board velocity is just totally puny and negligible. So kind of everything will fall out from this, picking these scales and non-dimensionalize the equations. And there's a couple things we have to understand that we don't know, right? What we don't know is we don't know what the scale of this boundary layer is. Before I gave you examples of that, I knew that the boundary layer for an airplane was like the size of a credit card, and you'll see how I can get that. The other thing we don't know is I said that u equals this velocity, but for that y velocity, I don't know what that looks like. So maybe I'll call it v infinity. It's actually pretty bad. We'll just call it capital V. Right, so these are the things we don't know. And we're going to use scaling to figure out what this is, what the y velocity is. And we're going to use continuity.